Hello, students. Welcome back to my lecture on topic 4.1, oscillations. In this topic, we'll be talking about simple harmonic oscillations, time period, frequency, amplitude, displacement, and phase difference. We'll be looking at the conditions for simple harmonic motion. What are the applications and skills? It's qualitatively describing the energy changes taking place during one cycle of an oscillation. So you should be able to describe the energy changes taking place during one cycle of an oscillation and also calculate the energy at different points. So at any point of the oscillation, you might be asked to calculate what is the potential energy and what is the kinetic energy. You should be able to sketch and interpret graphs of simple harmonic motion. Now, as far as the data booklet reference is concerned, the only formula that you are given in this topic is time period, and time period is 1 over frequency. You should be able to plot displacement time graphs, velocity time graphs, acceleration time graphs. So let's try to understand what is an oscillatory motion. So oscillations are vibrations that repeat themselves. For example, this is vibration that repeats themselves. So oscillatory motions are periodic motions. They repeat at regular intervals of time. There was one question asked that all oscillatory motions are periodic, but not all periodic motions are oscillatory. What does that mean? You might be asked to explain the statement using an example. So it states that all oscillatory motions are periodic, but not all periodic motions are oscillatory. So you see any oscillatory motion, for example, in this case, a simple pendulum, that is periodic motion. It repeats itself at regular intervals of time. But the second part of the statement was, not all periodic motions are oscillatory. And it makes sense because if you think about the motion of planets around the sun, or the motion of the moon around the earth, it is a circular motion. It is a periodic motion, but it is not an oscillatory motion. So all oscillatory motions are periodic, but not all periodic motions are oscillatory. And another example of an oscillatory motion would be a mass connected to a spring. So this is also an example of an oscillatory motion. And if you see here, at the extreme position, the velocity is 0. If you see here, the extreme position, the velocity is 0. The velocity is maximum at the equilibrium position. At this position, you see the velocity is maximum. So at the extreme position, the velocity is 0. It means that the kinetic energy is 0 at the extreme position. And if the kinetic energy is 0 at the extreme position, it means that the potential energy is maximum at the extreme position. We'll take those equations of potential and kinetic energy in more detail. So here you see, you can see that the velocity is 0 at the extreme position. So these are some of the examples of oscillatory motion. So oscillations can be rapid vibrations, such as a plugged guitar string or a tuning fork. Now let's try to understand some of these terms. What is time period, what is amplitude, and what is displacement? So let's talk about the amplitude. So here you see the amplitude is the maximum displacement. So from the equilibrium position. So this is the equilibrium position. And if you look here, the maximum displacement from the equilibrium position, so that will be amplitude. In this case, the maximum displacement is 4. So your amplitude is going to be 4. So amplitude is the maximum displacement from the equilibrium position. So as you see, this is the equilibrium position and this is the maximum displacement. Now, what about time period? The time period is the time taken for one complete oscillation. So if you see here, you can start from any point. So let's say we start here. So yes, start, and then you see the time it takes to go all the way here and then come back to its original position. So this is one time period. So time taken for one complete oscillation, that is called as the time period. And displacement, so the maximum displacement is the amplitude, and at any point t, the displacement could be calculated from the equilibrium position. So you could calculate what is the displacement from the equilibrium position. Always remember that the displacement is calculated from the equilibrium position. Now, frequency is the number of oscillations made per second. So how many oscillations are made per second, or how many oscillations that the oscillating object makes per second is the frequency. It is also considered as the cycles per second. And frequency is 1 divided by the time period. So there is a mathematical formula for frequency, and frequency is equal to 1 divided by the time period. Frequency is measured in hertz. So let's say if you have a question, the cycle of the previous example repeated each 24 seconds. What is the period and the frequency of the oscillation? So period is 24 seconds because it repeated each at 24 seconds. So the time period is 24 seconds. Then what is the frequency? So frequency is 1 over time period, and 1 over 24, that will give you the frequency, and that is 0.042 hertz. Now, phase difference. Now, let's try to analyze these two modes. Now, if you look at these two springs and masses connected to end of the spring, you see all the different parameters that we talked about, be it amplitude, be it time period, be it wavelength, they all are same. So how are these two motions different? Well, there is a phase difference. If you see, now here, this is stretched, and this is the starting point. So at time t equals to 0, this is where the mass is. And this one is compressed, and at time t equals to 0, the mass is here. Now what will happen is, you see that this object is going to go all the way here and then come back here. So what, and meanwhile, this object is, this mass is ahead of this mass by 1/4 and 1/4. So that's half of a cycle. If you see, this one is already ahead by half of a cycle. What I mean to say is, if you look here, this is already at this position. Now this object would reach here, and this is already here. So there is a phase difference of half of a cycle, and half of a cycle is 180 degrees, which is pi. So the phase difference, pi radian. So the phase difference is pi. So they have a difference of half of a cycle, and that's the phase difference is going to be pi, because one complete cycle is 2 pi. Now let's have a look here. You have this mass which is stretched and then released, and this one is start unstretched and left, and it is pushed to the left. So this one is being pushed to the left, and this one is being stretched and released. Now, if you look here, at time t equals to 0, this one is already ahead of this by 1/4 of a cycle. Since this one is ahead of this by 1/4 of a cycle, and 1/4 of a cycle is 90 degrees, which is pi over 2. So the phase difference is let's take up another example. Now this one is stretched and then released. So you see this one is stretched and then released. This one is pushed to the right. So this is pushed to the right. So this will be moving in this direction. So this direction, and this one will be, since it is stretched and then released, so this one will go in this direction. So if you see here, at time t equals to 0, this mass is here and this mass is here. Now, this will go all the way here and come back here to catch this one. So technically, this one is ahead by 3/4 of a cycle. So this is 1/4, another quarter, and another quarter. So this one is already ahead by the first mass by 3/4 of a cycle. So the phase difference is 3 times 3 over 4 multiplied by 2 pi. So that's 270 degrees. So that's 3 over 2 pi. Okay, now what are the conditions for simple harmonic motion? So the definition for simple harmonic motion is, in case of a simple harmonic motion, the acceleration is proportional to displacement, or acceleration acts opposite to the direction of displacement. For example, if you see here, this is the equilibrium position. Now, as you see, as the displacement increases, so let's say if we move to the other side, so as the displacement increases, the restoring force increases. So the restoring force is proportional to the displacement. More the displacement, more it will be the restoring force. So restoring force is proportional to the displacement. And if you see, the restoring force acts opposite to the direction of displacement. If the displacement is towards right, the restoring force acts towards left. So the conditions for simple harmonic motion are the force, or you can say restoring force. Restoring force is proportional to the displacement, and restoring force acts opposite to the direction of displacement. It could also be said acceleration is proportional to the displacement, and acceleration acts opposite to the direction of displacement. Now you have a question here. A spring having a spring constant of 125 Newton per meter is attached to a 5 kg mass and is stressed 4 meter. And this is stressed 4 meter from rest using Hooke's law, so that the acceleration A of the mass spring system is related to the spring's displacement. X by proportion A is proportional to negative X. So you can think this way. Here the force, that's the restoring force, is proportional to X, because there is, as X increases, as X which is towards the right, as X increases, the restoring force increases. But the restoring force is a vector that acts towards the left, and the displacement vector acts towards the right. So you could say F is proportional to negative X. Now, since F is mass times acceleration, you can divide them by mass, and you will get acceleration is proportional to negative X. So here you see F is equal to negative Kx, because if the displacement is acting towards right, the restoring force is acting towards left. So F is equal to negative Kx. F equals to ma. So ma is equal to negative Kx, or A is equal to negative K over m times X. And because K is a constant, m is a constant, you can say A is negative constant times X, or A is proportional to negative X. Now, you are supposed to write an equation for this example and find out the acceleration of the mass when X is equal to negative 2 meters. So, and again, that is part C. What is the displacement of the mass when the acceleration is negative 42 meter per second square? So you can start with A, we derived in the previous example, A is equal to negative K over m times X. That's the formula we derived from the previous slide. You see, A is equal to negative K over m multiplied by X. Now, in this case, when X is negative 2, I can just substitute X as negative 2. And here, K was 125. That's given in the question, 125. And if I go here and spotlight, okay. So you see K is 125. So K is here 125. Mass is 5 kg. Mass is 5 kg. And X, they said, was negative 2. So you substitute in negative 2, and you will get 50 meter per second square. Now, for the second part, find the displacement of the mass when the acceleration is negative 42. So this time they have given you the acceleration. Your standard equation is A is negative 25x. So A is negative 25x. Your acceleration is negative 42. So negative 42 would be negative 25 times x. And you can solve for x, and you will get 1.7 meters. So as far as the definition of simple harmonic motion is concerned, you will have to write acceleration is proportional to displacement, and acceleration acts opposite to the direction of displacement. Remember, this question is always asked in IB exam. Define simple harmonic motion. And the definition, although this is a definition question, but it is a 2-marker question. So in order to get both the marks, you will have to write acceleration is proportional to displacement and acceleration acts opposite to the direction of displacement. So that is what it means when you write mathematically A is proportional to negative x. It means that acceleration is proportional to displacement and acceleration acts in the opposite direction to the displacement. And these are the conditions for simple harmonic motion. So you see, if you have the displacement on towards the right, so if the displacement is towards right, which is positive, the restoring force is acting towards left. So if the displacement is towards right, the restoring force is acting towards left. So that is why we say F is proportional to negative x, because the restoring force acts opposite to the direction of displacement. It acts opposite to the direction of displacement. And you could say F is proportional to negative x, or MA is proportional to negative x, or A is proportional to negative x. Now, this is how you could represent the graph of a simple harmonic motion. What you can understand is, like, let's say this is a mass connected to a spring, and imagine that there is a marker connected to this mass. And as this mass oscillates, a sheet of paper is moving towards left. And as the marker goes up and down, you will see how or what type of graph the marker draws on the paper. So you see it starts here, and now you could see a sine graph. So oscillations or simple harmonic motions could be represented by a sine graph. You could also represent a simple harmonic motion by a cos graph. And of course, this is the time period. This represents from this point to this point. So when you're connecting two consecutive points in phase, that is considered as the time period. Now we'll talk a little bit about energy. So the velocity of this pendulum is 0 at its extreme position. So it means that this has potential energy, maximum potential energy here, and kinetic energy is 0. Kinetic energy is represented by the red rectangle and the potential energy by the green rectangle. And you see what happens. As at the extreme position, the potential energy is maximum. As I release this mass, you see the potential energy starts decreasing and the kinetic energy starts increasing. When it reaches to its equilibrium position, the kinetic energy is maximum and the potential energy is 0. Have a look here. You see at the extreme position, the potential energy is maximum, kinetic energy is 0. At the equilibrium position, the kinetic energy is maximum, potential energy is 0. However, at any other position, the kinetic energy and potential energy both are combined. So if you were to calculate energy at any other point, it could be a mix of potential and kinetic energy. However, the total energy at every point is constant. It's as per the law of conservation of energy. So energy is conserved. So at any point, the total energy is constant. It could be a mix of potential and kinetic together, and it could be only kinetic, or it could be only potential. In my next video, we will talk about the mathematical equations that connect the potential and kinetic energy. I would advise you to watch this video carefully. You can pause and watch at your own pace. And if you like the content, you can click on the like button. Thank you.